This is Udit again from TechSpark with another session covering data engineering question and answers. And in today's session, we're going to discuss about shuffling and Apache Spark. So before starting off, I would like to give a brief overview of myself. I have been working in data engineering domain for almost 9 years with various projects and involved in creating data pipelines for several clients. I also train candidates in this field to help them build an interview-ready profile with our comprehensive course covering all the necessary topics of data engineering. So to understand what is shuffling in Spark, I believe you already know the difference between the narrow transformation and wide transformations, right? And when I talked about wide transformations, I said that it creates stages because there is the shuffling occurs. And this shuffling phenomena is something that kind of slows down the Spark application that is running in my Hadoop cluster or even in the cloud. So let us just give a brief summarize of the Apache Spark shuffling. It refers to the process of redistributing data across different nodes in a cluster to execute certain operations such as aggregations or looking up of data. It occurs generally when wide transformations like group by key, reduce by key, join, distinct, these kind of transformations are performed, requiring data from multiple partitions to be aggregated or combined. So if you look at the picture on the right side, so I have two stages. One is stage one, stage two. So this is the initial data that I have. If you see, there are different keys, and first I'm trying to do a map operation, and as you all know, that map is a narrow transformation. So all these operations, all these transformations are being acted upon each and every individual partition. Okay, each and every partition has nothing to do with the other partitions, and that is the reason it is quite a smooth and faster approach. So in the stage one, if you can see, there are different keys are being highlighted with different colors. So like this over here, the red or the orange color is a key, and then there's the yellow is another key, and then there's this ash color or gray color, which is another key. So now in the second stage, when I call a group by or reduce by or any such operation, the white transformation, which usually causes this shuffling or which causes another stage to be created. In that case, what you're seeing over here is now the each and every partition is been taken. Sorry, each and every key has been taken from each and every partition, and they are being accumulated or they are being assembled from different other partitions as well. Like if you see over here, if I try to do a group by operation on this key, which is being highlighted as the orange one, in that case, this one is coming from the first partition, and from the second partition, there are three other keys that are coming in. Similarly, if you look at the yellow key, from the first partition, there are two keys coming in. From the second partition, there is one more key coming in, and from the last one, there is another three partitions. Sorry, another three keys are coming in. So from each and every partition, the data has been jumbled across. Okay, jumbled across, and they're forming other partitions. So this is what shuffling means, and this is it usually is being occurred whenever a wide transformation is called upon. And if you see this stage one, okay, this stage one could have continued if I had called only narrow transformations upon them and no wide transformations. The moment I call a wide transformation upon this stage one, another stage, which is the stage two gets created, and the data is being shuffled over there. Okay, so this is the phenomenon which is known as the shuffling, and this takes a bit of toll on the Spark application. And we're gonna discuss about the challenges that we face whenever we call a shuffling. So let's go one by one for each and every point. Okay. So the first one is the network overhead. So data needs to be transferred between nodes, which is costly in terms of bandwidth and latency. Obviously, since the data is going to be jumbled across all the nodes in the cluster, it's gonna take some toll on the time and the efficiency in the job. So that's what is happening. So whenever a new stage is getting created, you see a minor lag in the Spark job. Had it been a Spark API or an application you have written only based upon narrow transformations, in that case, you would have seen the job getting completed much faster. So this is the first challenge. The second thing is the disk IO. Now you have to remember whenever you do a shuffling, then a certain portion of the data or whatever the shuffled data is there, it will be stored on an intermediate disk, which is known as the shuffle disk. and from this shuffled disk, it's get again written to the newer partitions. Okay, so whenever a new stage is created or any shuffling happens, new number of partitions get created. Now, what is that number of partition and how can we tweak that? I will discuss that as well in this session. Okay, but the thing is, if the amount of shuffled data exceeds the available memory, Spark writes the data to disk, which slows down the performance. Now, as I have told you when I was covering the fundamentals of Apache Spark, the reason why we shifted from MapReduce to Apache Spark is because Apache Spark is majorly a memory, in-memory computing engine, right? It stores the intermediate it stores the intermediate result into the memory, which is the RAM of the system, instead of the disk. Had it been the disk, in that case, the I/O throughput would have increased furthermore. Okay, that was the problem with the MapReduce, because in MapReduce, the intermediate result gets written into the disk instead of the memory. Okay, so each and every time you read the data to and from the disk, it takes a heavy toll on the disk I/O. Also, the application slows down. So even with the Spark application, I see that I'm not able to utilize that that important feature that Spark has, the in-memory computation. And whenever I do a shuffling, in that case for heavy processing, the data is getting written into the disk. So that is also one more challenge that we see whenever we do a shuffling or whenever we call upon a wide transformation of a Spark API. Okay. The third point is serialization, deserialization. Converting data between its in-memory and on-disk forms adds computational overhead. So we need to understand what is serialization or deserialization. The thing is, whenever data is getting shifted from one partition to another partition, the data doesn't get shifted like that. Okay, so there is this process. First, the data will be converted into binary format data. Okay, what the computer understands. So that binary form of data then get transferred to another node or another partition, another container, so to speak. And then when it reaches over there, then that binary format data gets again converted into the actual data. I mean, it could be the string or integer, whatever data that we are kind of dealing with. So this transition from one partition to binary, then the moving across the node, and then binary to the main format. So this phenomenon is known as the serialization and deserialization. Serialization means it's the data converting from string to binary, and the deserialization is actually the opposite, from the binary format to string or integer. I mean, whatever be the uh, origin data type it was. Okay, so this whenever this happens, this realization or deserialization, automatically it takes a bit more time to job to process for any job. It could be Spark job or any other code that you have written, any other application, so to speak. So this thing also happens whenever we call the shuffle or whenever the shuffling occurs. So this is one more major point why the job gets slowed down. And then the fourth and also last but not the least kind of a point, that is the skewed data. Uneven distribution of data across partitions can lead to bottlenecks, as some tasks may process significantly more data than the others. So in layman terms, how a skewed data looks like is, suppose I have a data and over there is some employee details are there, and one of the columns say is an employee department. Over there say there is a department of IT, there is department of HR, and department of managers, etc., etc. Okay, so think of it that the IT has the most number of employees. So eventually, in the data, the number of records for IT department would be much more than the others, say 10x. Okay, so for each and every HR set, there are 10 IT employees. I mean, not four. Like if I try to map them against in order to compare them with the numbers. Okay, so in that case, what's happening whenever I try to group by with the department, so all the same group numbers will get into the same partition, right? So what is happening for IT? Suppose there are like 10,000 records, and for HR there are like 100 records. So those 100 records is getting into one single partitions, and that 10,000 records is getting into one single partition. So now if I try to do a simple mathematics, okay, so I have 100 records at one side and 10,000 records at the other side. So which one will take faster? Obviously the 100 So I'll see that the HR department or the HR data is getting processed so fast But on the other hand, the IT department data is taking so long, it's taking say like hours to process. So this is the skewness. Skewness is it's like the uneven distribution of the data across the partitions, because some partition has like 10,000 data, the other partition has like 100 data. So this is another reason why I mean the shuffling can decrease the performance of the Spark job, and these are the challenges that we should always keep in mind whenever we're calling in a white transformation. Even though in some cases white transformation is required, there is no other there's I mean no other option for us. But the thing is, there are some ways we can reduce the IO, or there is some ways we can optimize a job a bit faster, and let's look at those examples as well. Right. So how can we optimize the partitioning, or how can we optimize, or how can we improve this shuffling process, whatever this inevitable phenomenon is that we are dealing with? Okay, first of all, use operations like repartition or coalesce to control the number of partitions explicitly. Okay. Now, see, whenever a shuffling is occurring, there is a certain number of partition that gets created by default, and that is 200. Okay, there is one point that I'll talk about it. So by default, it is 200. The thing is, in some cases, I may not need 200 number of partitions. In some cases, I may need even more than that. That's totally upon the requirement. That's totally upon the input data that I'm dealing with. So if I use the repartitioning in case where I need to increase the number of partition for bigger data or larger data, in that case I can do that. Also, if I don't want 200 partitions, I want less than that. In that case, I can do a coalesce. Coalesce will simply decrease the number of partition. So using these two features, or using these two methods, I can tweak the number of partitions, and that will also help me in completing the Spark job much faster. Right. Second is use partitioning strategies that align with the data processing requirement, like hash partitioning for this. So whenever you hear the term hash, so it kind of works like bucketing in a hive. In case of bucketing of hive, I have shown you like there is this hash formula, which is kind of like the number of buckets divided by the column ID. Sorry, I just said the opposite. It's the column value ID, the column value divided by the number of buckets there are, and the remainder will be the nth bucket, or I mean that bucket where that particular column value will be shifting it. Right? I totally paint the whole picture how it happens when I was explaining the hive bucketing. So if you use a partition strategy like that, in that case, what will happen? So I'm taking again that example, right? For IT, it's all going into one single partition, and it is creating a skewed partition. So in that case, suppose if I try to add a random number after the column ID, let's say it is like 1 2 3, it's gonna append after the column value ID. Then how it looks like, the data will be IT1, IT2, IT3, like that. Okay, in that case, IT1 and IT2 is not same. So they will go into different partition. Okay, so this is called the hash partitioning way. In that case, we can somehow reduce the number of partition, or we can deal with the skewed data. That term is known as salting. Okay, so salting is one of the ways we can deal with the skewed data. Third one is use operations like map partitions or reduce by key instead of group by key to aggregate data before shuffling. So map partitions or reduce by key is also wide transformations. Okay, but still it's better than group by key to aggregate the data. The reason being, map partitions or reduce by key, both of these two transformations works in a bit different way than that of group by key or join for that matter. Okay, so how it works, if I try to call upon map partition or reduce by key, first the sorting or aggregation will happen on the partition level. Then the data will be moved across the cluster. Meaning, suppose there are like 5 different partitions, and each partition there is this ID data. So partition 1 has 10 ID data, partition 2 has 20 ID data, and so on. So if I do a group by key, in that case, from each and every partition, the ID data will move across the nodes. The serialization and everything will happen for all the data for each and every partition, and then it will be stored into a different new partition. Fine. But If I do a reduce by key, what will happen at first inside the partition? In the first partition, say there are like 10 IT records. So first, those 10 IT records will be clubbed in and will be a one single. If for each and every IT record there the salary and combining up to say there are like 10 IT departments employee, and for each and every department salary there is like 10,000. So if I do 10 into 10, then simple mathematics, it's around like 100k, 100,000. So in each and every partition, it will be like one IT and 100,000 salary. Okay, now that partition level aggregation is done, then that data will be moved across the nodes. So instead of like 10,000 records, there will be like 10,000 divided by 5 records that will be moving in or getting shifted to the newer partition. So that's how we are kind of like reducing the overhead or reducing this lag of shuffling a bit. Then if we call upon the group by key, in that case, all of the data without the partition level aggregation will move into a new partition, or kind of like moving across the cluster, which will take much heavier toll on the job. Fourth one is avoid wide transformations when possible. Use narrow transformations that do not require data moving across the partitions. This is something is very self-explanatory thing, right? We have discussed about how narrow transformations are much simpler. It works on the partition level, whereas the wide transformation does the shuffling. So if possible, just use the narrow transformations only. But yeah, I mean, in real world project, we have to group by the data. We have to join data from different other sources. So like there is no other way other than using the wide transformation. So uh, I mean, we have to use the white transformations, but we have to tweak some other configurations as well, just to make sure that our job doesn't go into hours of running. Okay, so last one is probably the most valuable point, that since we're going to be using the white transformations no matter what, how can we use it in better way? Okay, so adjust the settings like Spark SQL shuffle partitions. By default, it is 200, or Spark default parallelism to match your data and cluster size. All right. So as I just mentioned, right, there would be 200 default partitions that will be created while while the shuffle operation happens. Now you see two different configuration. One is the Spark SQL shuffle partition. The other one is the Spark default parallelism. They both do the same. The only difference is whenever I'm using the Spark SQL or data frame API, in that case the configuration that works is the Spark SQL shuffle partitions. And whenever I'm using the RD API, which is kind of like obsolete and no one uses, but if you try to use that one, in that case you use the Spark default parallelism. So both of this will kind of like control the number of partitions that have been created at the time of shuffling. So since by default it will be 200, okay, and I don't need that number of partition all the time probably, and there could be some rare scenarios where the data is so huge that I need even more than that. So in those cases I need to do a repartition or coalesce to adjust the number of partitions. Okay, other than that, if I feel that 200 partitions is something that I need is optimal for my application, then I'll just keep it as it is. So these are the ways we can simply tweak the operations, or we can play with the configurations to deal with our shuffling strategy. Okay, and basically what I feel is this Spark shuffling is something that we have to use in our day-to-day data processing, and we just have to make sure that we in apart from the configurations such as the default parallelism or shuffle partitions, we also take care of the driver memory and the RAM executor cores, because at the end of the day it's how your job is getting paralyzed and on what iterations, even though with the different number of partitions getting created for each and every shuffling, how can we make the job complete faster? So to understand all these things, please do reach out to us. We're gonna show you how to submit a Spark job in application. We're gonna also help you write code using the Spark data frame API and using the window function, joining all the advanced SQL functions that will help you get acquainted with the Spark API, and also integration with these Hive tables as well. We have that data that is getting stored in the Hive. How can we read the data from Spark? How can we read the data from Hive? How can we process the data using Spark, and then write it back to the Hive. All these things we will cover in our data engineering course. So we mostly gonna cover all the necessary tools such as Spark, Hadoop, Hive, AWS with hands-on coding and real-world project. We also make sure that each and every candidate, his profile is built in a way that he is interview ready. He can not only crack the interviews, he can write code, and he can explain each and every operation in the field of data engineering very fluently whenever being asked in the interviews. So reach out to Expo to know more. For this session, I'm gonna sign off. Bye bye.
Contact us for the free job assistance. We will help you to get the IT job. Please like, subscribe, and share the channel for more regular updates from TechSpoke.